After the Big Bang, the dance of the universe's cyclical circulation began. Light and matter, like sparks in empty space, emerged and created the world. Time flows, drawing the splendid shadows of the universe, and stars continue to tell stories, passing them on through generations. The Big Bang, originating from the depths of the galaxy, has taken its place alongside the endless flow of time in the vastness of the universe. Our eyes catch a glimpse of the history of the universe, the dance of stars, the tranquility of galaxies, the birth and disappearance of planets. The universe beckons us with an unknown dialogue, and we are constantly captivated by its mysteries. Time envelops us as a gift, conveying traces of the past and descriptions of the future. Our understanding challenges the mysteries of the universe, but in the face of the infinite cosmos, our understanding is small and limited. Like stars departing as light, our ultimate destiny will one day return to the universe. The evolution of the universe, through the infinite tunnel of time, is advancing beyond our limits towards profound mysteries. Today, in the 6th session of Introduction to Astrophysics, let's explore how scientists explain the topics of energy, matter, gravity, and time. Subscriptions and likes greatly empower video production. The state of the universe before the Big Bang has not been definitively determined. However, based on current research results and hypotheses, it is estimated that the pre-Big Bang universe was in an extremely high energy and dense state. In this state, matter and energy would have exhibited quantum characteristics, and the phenomenon of mutual transformation would have occurred repeatedly. Therefore, it is challenging to simply state that there was only energy and no matter before the Big Bang. The pre-Big Bang universe remains a realm of unknowns in physics, requiring further research and experimentation. Dr. Hawking attempted to explain the pre-Big Bang using the no-boundary proposal theory. This theory suggests that the boundary conditions of the universe have no boundaries, and time and space originated from the Big Bang. Since time did not exist before the Big Bang, events before it cannot be defined, according to this proposal. After the Big Bang, there was a process of energy transforming into matter. In the early universe after the Big Bang, conditions were characterized by extremely high temperature and density. During this time, energy and matter interacted and transformed according to Einstein's famous equation E equals mc squared. In other words, energy converted into particles with mass, and vice versa, in a repeating cycle. Through this process, primordial particles were created, and they collided or combined to generate various forms of matter. For example, quarks and gluons combined to form nuclear particles like protons and neutrons, and nuclear particles combined with electrons to form atoms like hydrogen and helium. These atoms, influenced by gravity, came together to form stars and galaxies. This explanation covers the process of energy transforming into matter after the Big Bang. The Big Bang enables a deeper understanding of the origin and structure of the universe, as well as the relationship between matter and energy. This passage discusses the gravitational effects in fermionic and bosonic states or energy states. Fermions are particles with half-integer spin that follow the Pauli exclusion principle. Examples of fermions include quarks, leptons, and baryons. Energy states, in the context of quantum mechanics, represent the possible values of energy a physical system can have. These states are expressed in terms of quantum numbers, and lower energy states are filled sequentially. In fermionic or energy states, it is difficult to say that gravity exists inherently. Gravity, as described by general relativity, acts as a force on all matter and energy in the universe, curving space-time. Therefore, if fermions or energy states have mass or energy, they can generate and experience gravity. For instance, neutron stars or white dwarfs are celestial bodies supported by the pressure of fermions like neutrons or electrons. Despite their small size compared to their mass, they exhibit strong gravitational effects. However, the gravitational force in fermionic or energy states is considerably weak compared to other forces. Fermions are influenced by other fundamental forces such as strong force, weak force, and electromagnetic force, which are much stronger and determine the behavior and interactions of fermions. For example, quarks, influenced by the strong force, form composite particles called hadrons, and electrons, influenced by electromagnetic force, contribute to the formation of atoms. Energy states are determined by quantum mechanics, and the compatibility of gravity with quantum mechanics has not been fully elucidated. Quantum gravity theories attempt to describe gravity in a quantum mechanical framework. Bosons, on the other hand, have integer spin and do not follow the Pauli exclusion principle. Examples of bosons include photons, gluons, and gravitons. Bosonic states represent the possible states of a system composed of bosons. These states are distributed according to Bose-Einstein statistics, and bosons can share the same quantum state. Similar to fermions, bosonic or energy states do not inherently possess gravity. Gravity, described by general relativity, acts as a force on all matter and energy in the universe, curbing spacetime. Therefore, if bosons have mass or energy, they can generate and experience gravity. For example, photons, having energy and momentum, are influenced by gravity. Gravitons, hypothesized as the carriers of gravity, would also be influenced by gravity if they have mass. However, the gravitational force in bosonic states is weak compared to other forces. Bosons are influenced by other fundamental forces such as strong force, weak force, and electromagnetic force, which are much stronger and determine the behavior and interactions of bosons. For example, photons are reflected, refracted, absorbed, or emitted due to electromagnetic force. The gravitational force of bosons, like gravitons, needs to be described through quantum gravity theories, although there is currently no definitive evidence or theory. Gravitons are hypothetical virtual particles that mediate the gravitational force. Predicted by quantum gravity theories, gravitons have spin 2, no mass, and transmit only gravity. They interact with all matter and energy in the universe, creating the curvature of spacetime. Gravitons, however, have not been observed, and quantum gravity theories lack definitive evidence or consensus. Quantum gravity theory is a field of theoretical physics aimed at describing gravity in a quantum mechanical framework. There are several contenders within the realm of quantum gravity theory, each proposed by different scientists. For instance, string theory, developed in the 1960s by researchers such as Gabriele Veneziano, Yichiro Nambu, Leonard Susskind, and Holger Beck-Nielsen, represents all fundamental forces, including gravity, and particles as one-dimensional strings. Loop quantum gravity, formulated in the 1980s by Abhay Ashtekar, Carlo Rovelli, Lee Smolin, Ted Jacobson, etc., quantizes the gravitational field and represents spacetime as loops and networks. Causal dynamical triangulation, developed in the 1990s by Renato Lal, Jan M. Bjorn, Jerzy Jerkowitz, involves dividing spacetime into triangles, considering quantum fluctuations, and exploring the quantum aspects of the geometry. Entropic gravity, proposed in the 2000s by Eric Verlinde, describes gravity in terms of changes in entropy. Twistor theory, introduced in the 1960s by Roger Penrose, seeks to unify gravity and quantum mechanics using complex numbers and the concept of twistors. Stephen Hawking did not champion a specific quantum gravity theory. His contributions were focused on black hole-related research within the framework of quantum gravity theory. Hawking discovered that black holes emit radiation, a phenomenon known as Hawking radiation, and proposed various hypotheses related to the black hole information loss problem. However, Hawking did not claim to have completed or validated a quantum gravity theory. He considered his work as a step in the direction of quantum gravity theory but acknowledged the need for continued efforts to find a comprehensive theory. Hawking supported and encouraged ongoing endeavors to understand quantum gravity. Shifting the focus, the Higgs particle, discovered in 2012 at CERN's Large Hadron Collider, plays a crucial role in particle physics. It imparts mass to other particles within the framework of the Standard Model. The Higgs field, associated with the Higgs mechanism, pervades the universe, and the Higgs boson is the particle representation of this field. Regarding black hole entropy theory, physicist Jacob Bekenstein proposed in 1972 that black holes should possess well-defined entropy. This idea was later complemented by Stephen Hawking's discovery that black holes emit thermal radiation, contributing to the foundation of black hole thermodynamics. Various perspectives exist on how this theory might effectively explain the origin and evolution of the universe. One viewpoint associates the entropy of black holes with the overall entropy of the universe. Universe entropy increases with its expansion after the Big Bang, making it a crucial concept in explaining the universe's form and evolution. In summary, this discussion touches upon different quantum gravity theories, Stephen Hawking's contributions to black hole physics, the discovery and significance of the Higgs boson, and the theory linking black hole entropy to the universe's origin and evolution. History of Time by Dr. Stephen Hawking is a popular science book that introduces the latest knowledge of the universe and time in an accessible way. In this book, time is explained as one of the fundamental characteristics of the universe, essential for understanding all phenomena in the cosmos. Dr. Hawking argues that time is not absolute, but a relative concept that can vary depending on the observer. According to the general theory of relativity, gravity is a force that bends space-time. Therefore, the closer an observer is to a gravitational field, the slower time appears to pass for them. For example, an observer near a black hole would experience time passing more slowly than an observer farthest away from it. Dr. Hawking claims that time plays a crucial role in the origin and evolution of the universe. According to the Big Bang theory, the universe started approximately 13.8 billion years ago from a singularity, a state where time and space were infinitely distorted, and the laws of physics did not apply. Hence, a physical description of the universe before the Big Bang is deemed impossible. Dr. Hawking also asserts that time is significant in the end of the universe. If the universe continues to expand, it will eventually reach a state known as heat death, where all matter is scattered and the temperature becomes uniformly distributed, rendering time meaningless. In History of Time, Dr. Hawking provides various perspectives on time, contributing to our broader understanding. The specific content regarding time in the book can be summarized as follows. Time is not absolute but relative. Time plays a crucial role in the origin and evolution of the universe. Time is significant in the end of the universe. Dr. Hawking defines time in History of Time as follows. Time is the measure of the rate of change, and the passage of time measures the extent of change that has occurred. According to this definition, time is a tool for measuring changes in physical phenomena. Therefore, time is not absolute. It can vary depending on the observer's perspective. Dr. Hawking divides the history of time into 3 parts in the book. The beginning of our universe, explanation of the origin and evolution of the universe, focusing on the Big Bang, expansion, inflation, and dark energy. The nature of time and space, explanation of the nature of time and space based on general relativity and quantum mechanics. Covers the relationship between time and space, the direction of time, and the possibility of time reversal. The end of time, explanation of the possible outcomes for the end of the universe based on its expansion. Discusses possibilities such as the Big Crunch, Big Freeze, and Big Rip. These discussions contribute to a more profound understanding of time's essence and its role in the universe, as presented by Dr. Hawking in History of Time. After the prelude of the Big Bang, the cosmic dance began, illuminating the darkness and giving birth to the world. The evolution of the universe is an infinite symphony, with stars dancing at every branch of the galaxy, vividly described to us. The ceaselessly flowing time leaves behind mysterious traces of the universe, conveying life's story to us. In the depths of the galaxies, the cosmic festival continues, with planets and stars weaving tales in every moment. Those stars silently depart, we etch their departed traces onto the pages of time. The universe unfolds a book of hope for us, revealing the intertwined flow of past and future through the passage of time. Our understanding continually faces challenges, and in the infinite embrace of the universe, we become small lights, shining. Exploring the endless cosmos takes us beyond our limits, into the mystery of time and the universe flowing together. In this grand narrative, the cosmos and time entwine, creating a tale of beauty and wonder.